Welcome to the third lecture. So, today we will start this mathematical model of TEM mode. We have already expressed in equation 5, equation 15, we have already expressed all the transverse component in terms of two longitudinal components. Now, for TM to Z, the longitudinal components both goes to 0. Put this TM condition to equation 15. So, you see, if we put Ez 0, Hz 0, Ez 0, Hz 0, Ez 0, Hz 0, Ez 0, Hz 0. So, Hx, Hy, Ex, Ey, what happened? All the transverse fields, that is Ex, Ey, Hx, Hy become 0. So, that means there cannot be any field. So, no electromagnetic field exists in the TM case. Have we made some problem? This solution, it is true that one solution to the Maxwell's equation is this, that all the fields are 0, but that is a trivial solution, that always happens. So, mathematically it is a solution, but physically not possible. That means TM mode cannot exist. Our mathematics says that. Let us once again see this equation. Now, we have said Ez, Hz all are 0. But what is this Kc? So, Hx will be 0 if this is 0 and Kc is not 0. But what is Kc? If you remember, Kc is, let us see whether I have this earlier thing. This is Kc. You see that Kc is, it can be 0 also, because Kc square is equal to K square minus beta square. So, if K is not equal to beta, then okay, all electromagnetic fields are 0. But if K is equal to beta, so you see that when Kc is 0, then this becomes a 0 by 0 case. So, 0 by 0 may have some value that we know, L hospital and all those. So, I cannot say that Hx is 0 always. Okay, if Kc is 0, Kc is not 0, let us write that Kc is not 0, then TM to Z field does not exist, no TM to Z. But Kc is equal to 0, it may exist. So, let us, we will have to go back and see more carefully. So, that we will do. So, since we will need to go back to Maxwell's equation with this TM condition to determine the TM field distribution. So, this is the first thing you remember in modeling TMZ, that do not falter on this, that do not say that a ratio numerator by denominator, you have learnt in your school days 6, 7, but we forget many times. So, from equation 13, you refer to notes, we can write this for TM mode, and this we get that you see from Maxwell's equation it is coming that k square may be equal to beta square, and in that case Kc becomes 0. So, it is a possibility for TM mode, this is possibility that Kc is 0. That means, what we say the cutoff wave number of TM wave is 0. Now, this is very advantageous. What it says, as I said while explaining the cutoff wave numbers physical significance, that it is it says that the cutoff will happen at particular number. So, that cutoff wave number is the frequency is reciprocal of this. So, what it says that all possible things, that means starting from Kc is equal to 0 to Kc any value, you can have Tm. This implies that frequency even a DC or very near to DC small frequency signals also can be propagated as TM modal fields. So, for TM mode Kc is equal to 0, K is equal to beta, that means wave number is equal to the phase constant. For other modes it is not true, but this is the only mode where this is true, and that is why we need to revisit that we are getting all the transverse fields as 0 by 0 case. So, we will have to go to the basic equation Maxwell's equation and find that. Now, in Maxwell's equation there is a problem, that you see Maxwell's equation, the first Karl equation relates del cross E is equal to that del B del T. Second equation del cross H is equal to J plus del D del T. So, basically you see electric field is related to magnetic field, magnetic field is related to electric field, but both are unknown to me. So, from any of these equation I cannot solve for neither electric field nor magnetic field. So, we need to do some manipulation. So, as I said, Maxwell's equation relate either electric field to magnetic field or vice versa, but for solving we need to express electric field in an equation where no other unknown, for example, magnetic field should not be there in that equation. Then only I can solve, because in an equation we can solve when one unknown is there, all others are known. But if electric and magnetic field both are there, both are unknown, so I cannot solve. Now, who does that? You all know that if we take the curl of the first equation and put it into the second equation, or curl of second equation and put it in the first equation of the Maxwell's equation, we get a equation where either electric field is there or magnetic field is there, and that equation takes this shape del square E plus omega square plus omega square mu epsilon E is equal to 0. This is called wave equation or Helmholtz equation, because Helmholtz, a famous scientist, he first gave the solution. So, you can easily derive it, as I said, and also you can see our notes, equation 18 to 20 will show you this. So, this equation can be solved, because you see del square E plus some constant into E is equal to 0. So, it is a second order differential equation, second order differential equation in E. Also, all wave equations like all the our H, our potentials, they also equal, the vector potentials, they also equal like this. You know that we have a magnetic vector potential that will obey this. So, we know how to solve second order differential equation, that is why in maths we were taught that. So, we will be able to show that. So, now also for lossless medium, that means if we initially we will try to find these TM fields in lossless medium, then there will be a lecture on loss, how to incorporate loss, etc. So, for lossless medium, we know that lossless means the basically sigma that is infinite, that means conductivity is infinite. So, in that case permittivity, permeability both are real. So, these unknowns, omega square is definitely real quantity, and this one is a product is a real quantity. So, this whole constant is real. So, we can always solve for this. Now, there are many solutions to this. One of them is the already you have seen familiar equation, that is plane wave solution. So, that Helmholtz equation for TEM wave, this one, this has various solutions. Please remember that plane wave is one such solution. We will first see the plane wave solution, then we will see the general solution for this. So, plane waves will satisfy this. Now, what is plane waves? The electric field uniform plane wave solution, sorry, I should have said already familiar uniform plane wave solution. Uniform plane wave means electric field is uniform, that is no variation with x and y direction in the transverse plane. So, what will happen to that vector Helmholtz equation? This is a vector equation, this is a phasor, but this is basically a vector, obviously it is a field. So, this is a vector equation, it has got 3 components, but fortunately in this case that will become a scalar equation in TEM case. So, for uniform plane wave, let us say the electric field is x directed. So, we are writing E is equal to x directed field, and uniform, that is why del x del y is equal to 0. As I said, uniform plane waves mean in the it does not have any x y variation, it is x directed, but variation x y is not there. That means del x is equal to del x is equal to 0 and del y is equal to 0. So, you put that into Helmholtz equation, this equation, because this del square means del 2 del x 2 plus del a 2. So, if you put that, it becomes simply this. So, we know how to solve this equation, this second order equation. Its solution will be E x is equal to some constant into e to the power minus j k z, because it is del z square, that is why E x will be e to the power minus j k z plus e to the power plus j k z with some 2 constants e plus and e minus. Now, e plus e minus you will have to determine, those are to be determined from the boundary condition. So, as we said that time, we have got the phasor, this is the phasor, though we have not put the tilde, but this is the phasor, no time. So, to put time I can come back. You see here what I will have to do, this whole thing I will have to multiply with e to the power j omega t, take the whole things total multiplication, that real part that we have done, and that becomes this. So, plane wave, its E x is this. So, I know electric field, let us put into the magnetic field, to find magnetic field, put it into Maxwell's equation. So, we put it and magnetic field becomes H y, it was E x, it is a H y in this form, equation 23, and the ratio of these two, the electric field by magnetic field, that you can see from this is the earlier one 21, equation 21 is the sorry, this equation it is the electric field phasor divided by the magnetic field phasor, that will give you the wave impedance to be eta. Now, we know that this is free space propagation. So, eta naught, its value is 377 ohm or 120 pi. From equation 22 and 23, you should note that for plane waves, electric field is orthogonal to the direction of propagation. Direction of propagation is z, electric field is E x. So, orthogonal. Magnetic field is Hy, Z is the direction of propagation. So, magnetic field is orthogonal to the direction of propagation, and electric and magnetic fields are also orthogonal to each other. Obviously, Ex and Hy, so they are also orthogonal. So, they satisfy plane waves, we have solved them. Now, we see that they satisfy the criteria of TEM modes. So, all plane waves are TEM waves. We have seen how plane waves are created. We have seen if you have an infinite sheet of current, you can have plane waves, or from any point source, if you are far away, you have plane waves. Far away means a reasonable distance away, you becomes plane waves. So, all plane waves, we know they are TEM type of waves. So, the transverse electromagnetic wave, and you have seen its structure. What is the Ex Hy? Hy is like this, Ex is like this, or if you want the real time signal, Ex is like this, Hy will be, you can easily write, okay, that it will be also cos same thing, only E plus by eta, E minus by eta, cos omega t and thing. So, you know its structure, but this is not TEM, plane waves are TEM waves, but TEM waves not necessarily are plane waves, all TEM waves are not plane waves. So, reverse is not true. So, what are the other solutions? Okay, plane wave solution was one solution, that means we have assumed uniform variation, etc. That may not be true. So, TEM waves can have field distribution much different from plane waves. So, also let us see what is the phase velocity of the TEM mode. So, for you see the phase velocity. So, what is the equiphase point? E to the power. So, here you see omega t minus kz is the phase. So, equiphase points. So, we know, let us observe a fixed phase point, that means omega t minus kz, that should be constant. Now, you know the definition of phase velocity. Phase velocity Vp is dz dt. So, in place of z, what is z? Omega t minus constant by k, d dt of that. So, that becomes omega by k. K we have already seen, the k was a constant we defined, that constant is omega into this. So, omega by omega into this. So, 1 by this. But what is this? This 1 by a, if you put the value, we have already seen the values, that becomes c, the speed of light. In free space, if you put those values omega epsilon, it becomes 3 into 10 to the power 8 meter per second, that is the speed of light. So, phase velocity of this TEM mode, that is light. So, TEM modes, they propagate their phase velocity, they propagate with light speed. And what is the wavelength of TEM mode? We know the TEM mode, any wavelength, distance between 2 points on the TEM wave whose phase differs by 2 pi. So, one is omega t minus kz minus omega t minus k z plus lambda, lambda is the wavelength, and this difference should be 2 pi. Solve, that becomes Vp by f. So, phase velocity, if it is in free space, c into 10 to the power 8 meter per second divided by frequency, you make, that becomes your lambda. So, that all you know, that how to find lambda. So, if I have 1 gigahertz signal, 1 gigahertz TEM wave signal, then what will be the velocity? 3 into 10 to the power 8 by 10 to the power 9. So, 0.3 meter. Okay. Now, let us come to the general solution of TEM mode. Plane wave is one solution of Helmholtz equation for TEM wave. The general solution admits, so uniform plane wave means we assumed uniform x, but now you can have both EXUI component and non-uniform. they need not be uniform, can have x and y variation. So, Ex should satisfy the scalar Helmholtz equation, this del del x square plus del del l square plus del del l square plus k square Ex is equal to 0. So, this equation we should solve. Now, we know that z variation is given by e to the power minus j beta z. So, del del z square is this. So, by that equation 24, that means this equation. Now, this is for Ex, also Ey will have some type of equation, because the general solution both Ex Ey possible. So, I have this. Where is the other part going? The k square. You see del del z square, that is giving me what? E to the power minus j beta z. So, that is giving me minus j beta into minus j beta, that is minus beta square. So, minus beta k square minus beta square, but for TM wave we have already proved that what is its beta? Where is that gone? Beta is equal to k, which slide? You see that beta square is equal to k square, we have proved from basic Maxwell's equation, it is always true for TM wave. So, minus beta square plus k square, that is why that is going. So, we are getting equation 25 and 26. Now, if we combine, we can write del t square Ex y is equal to 0. Similarly, you can do this for magnetic field. And now, what is this equation? Del t square means del del x square plus del del y square into this. So, this is the Laplace's equation. So, transverse TM field structure is similar to static fields, because in electrostatics we have seen that electric field and magnetic field, they satisfy Laplace equation. So, transverse fields, though they are dynamic fields, but their field structure, because you see this is a fundamental thing, that equation, a particular type of equation, its solution is also the same. So, if two equations have two equations of two variables, they have similar equations, then their solution will also be similar. This is a fact of mathematics. So, if transverse electric field or transverse magnetic field, they are satisfying this equation, means they are satisfying Laplace type of equation. So, and we know that electrostatic fields satisfy Laplace type of equation. So, solution of them will be similar. At the most they can be differed by some constant etc., but the solution is same. So, that is why these TM fields are called quasi static field, like static field. Quasi means it came from some foreign language, I do not know, but quasi means similar. So, quasi static, like static fields. So, TM fields can be expressed like the electric field, electrostatic field. Now, electrostatic field, we know that we can define a scalar potential for that. Okay. So, that means that the transverse electric field can be written as gradient of a voltage, but to do that we need to prove one thing. You see that if we write it as gradient of this transverse operator, we will have to prove that the curl given by the transverse operator of this transverse field E x y, that is 0, because that is the basis that electrostatic field satisfies, that curl of that electrostatic field is 0. That is why we say it is a okay, it is a conservative field. So, it can be written as a gradient of a electric field, can be written as a gradient of a potential or scalar function. But Here you see we are writing it as a different operator. Please remember, this is not a curl operator. Sorry, this is not a gradient operator. This is transverse gradient operator. It's not 3-dimensional, it is 2-dimensional. So we'll have to reprove that the curl or transverse curl, I should say, transverse curl of transverse field, that should be 0. Then only we can say this. So let us see. Go to Maxwell's equation. This is the Maxwell's first equation. This is E, this is H, this is transverse E. Please remember, this is the 3-dimensional E. We know that can be written as the any 3-dimensional vector can be written as a transverse component plus a longitudinal component. In case of TM electric field, the transverse longitudinal component is 0. So that's why we can write this equal to the curl of transverse operator, and that is this, because H also is only transverse. Now you expand. Now you see that this is right side is does not have any z component, left side we have written del cross this transverse electric field. So it has a k component. Now to satisfy this equation, this part should go to 0, this part should go to 0. So k component must be 0. So we can write that. Now let us see what is our required one, that transverse curl of transverse field. If you do the mathematics, it becomes k of that. Now this is 0. So put that here. So it does not have any k component. So we can say that del t cross E, the whole thing goes to 0. So that is also 0. So we have proved from Maxwell's equation, we have proved that transverse curl, I emphasize not curl, curl is a 3-dimensional operator. This transverse curl operator, transverse curl of the transverse electric field of TM wave, that is 0. Once I prove this, I say okay, I have proved this, so I can write this. So I am justified in writing 29, and now we say we are theoretically justified to introduce the concept of scalar potential even in the dynamic TEM case. No one can stop us. We have proved all the mathematics. So now we will write Exy as this, equation 29 again. Further, using Maxwell's third equation and the above potential. So this you see notes, these are mathematical details. This also obeys Laplace equation. Hence, once anything obeys Laplace equation, we can write it as so. If a TM wave is propagating to a 2-conductor line, we can always define a voltage difference between, which is nothing but the potential of conductor 1 potential minus conductor 2 potential. So it is equal to 1 to 2 E dot dl. So we can, if we know the electric field, we can find the what is the V12 as a line integral from first conductor to second conductor. Now this, so we know the structure. So we have told you how to do it, and also there is a, so similarly we can also define a current from the magnetic field by having a contour integral along any closed path. So that means we can define the TM wave by voltage and current definition. Now multi-conductor transmission line. So TM wave exists in 2-conductor transmission line. TM waves also exist in multi-conductor lines. This can be proved. Plane waves exist in free space. We have seen that if you are far away from any radiating source, you get plane waves. They are TM waves. they can be thought of as supported by two infinitely large conductors separated by infinity. But TEM waves cannot exist in a single closed conductor. Instead of two conductors, if you have a single conductor, TEM waves cannot exist. Why? And a single conductor example is a waveguide. You see, a waveguide is a pipe, so it is a single closed conductor. Why? Because in the single closed conductor, that equation you see, that if you are a single conductor, that means your potential of one conductor and potential of two conductor, they are same. So, V12 is 0. The moment V12 is 0, what happens? The scalar potential is 0. So, its gradient, that is 0, that means E becomes 0. Once E is 0, H is also 0. So, no TEM wave. If voltage is 0, then you put it here, gradient of that voltage, that is also 0, that means electric field is 0. Once electric field is 0, put it into Maxwell's equation, magnetic field is 0. So, in a single conductor, V12 is 0. So, E, that means transverse electric field does not exist. So, electric field does not exist. So, magnetic field does not exist. So, TEM waves cannot exist in waveguides. Any form of waveguide, waveguide means a single conductor, a metallic pipe of any cross section. It can be circular, it can be rectangular, it can be elliptical, any, its cross section is uniform, it is a single pipe. So, there TEM waves cannot exist. Then current, as I already said. So, let us summarize in last two slides what is the procedure for analysis of a TEM field. Solve Laplace's equation for Vxy. The solution will contain several unknown constants. Find the conditions from the boundary conditions for the known voltage on conductors. Then from equation 29, find E. You know equation 29 is that one, this one. So, once you know V, take the gradient, that will give you the electric field, transverse electric field. Then E from equation 9, you see your notes that if you know E, then we have already written the total field in terms of transverse field per longitudinal. Longitudinal is not here. So, transverse I know, multiplied by e to the power minus j k z, that is the E. Similarly, find H from equation 37, we have manipulated it a bit, and H from equation 10. You see your notes, I will upload that. So, from there you can find E and H, and compute V from equation 33. So, you can always find this. From here you can find, once you know E, you can find V easily, and I from equation 34. Then find phase constant of the transmission line is given by equation 17. Let us see hurriedly equation 17. So, you phase constant is coming, once you know K, so which is the frequency and the material constants. So, from that you can find beta, that is the phase constant. So, phase constant of the transmission line is given by equation 7. So, that is all. Now, we are assuming lossless. If lossy things, we will see in a separate lecture how to find this, all these things. And we have seen the impedance is equation 35 or 36, let us, that will come later. Impedance also we will discuss in another lecture, and characteristic impedance of any TEM line. Please remember this characteristic impedance is, you have found V, you have found I, take the ratio, that is characteristic impedance. Now, why it is called characteristic impedance? Basically, characteristic impedance is defined for a symmetric two-port network. Any symmetric network, what is characteristic impedance? That actually any non-symmetric also, any general two-port network that has image impedances. What is image impedance? That suppose I have a source resistance. Now, I have some load, so that from the source side the input impedance is matched with the source. Now, I reverse that, I put the image of that impedance, it is a pair of impedance, that in the source side, and from the output side I see that the output impedance that is same as the load impedance. Now, for a symmetric two-port network, these pair of image impedances, they are equal, and that is characteristic impedance. So, what happens to characteristic impedance? That means, if I terminate any two-port network with a characteristic impedance, then the input impedance seen at the input port is same as characteristic impedance, and that value you can calculate for TEM wave. You know V, you know I, so you can calculate Z naught characteristic impedance. Usually a TEM line is specified in terms of its characteristic impedance. Now, we will discuss characteristic impedance and other impedances in a separate lecture. So, I think we have completed this, how to analyze what is the mathematical model is now complete, that you know. So, start from Laplace's equation, solve for this, find out E, find out H, then you find out V and I, you find out beta, that is all, and also you can find out the wave impedance, that we will see later, and characteristic impedance. So, that completes the analysis of TEM mode.